On October 23, 2025, something unexpected appeared in the amateur sky tracking network. Dozens of backyard astronomers comparing their raw images against NASA's orbital data noticed the same impossible detail. 3. Atlas. The interstellar object that had been following a stable, predictable path had shifted, not by noise, not by drift, but by intent. At first, the adjustment looked like an imaging error, but as night turned to night, the offset grew. Each new exposure revealed the object slightly ahead of where gravity alone should have placed it. Its brightness dipped, then stabilized, and for a moment a faint flash near the nucleus, something changed direction. NASA hasn't issued an official statement. The Jet Propulsion Laboratory quietly updated the orbital elements without a press release. But the amateur community caught it first, and this time the data is time-stamped, verifiable, and public. So tonight we're going to piece together what these new photos actually show, why they contradict every natural model we've built so far, and what this could mean for NASA's silent revision of 3I Atlas course. If you're following this story as closely as we are, hit like, subscribe, and tell me what time it is, where you're listening from, because what happens next may rewrite how we think about interstellar travel itself. It began quietly just after midnight on October 23, 2025. Across different continents, from Spain to Chile, from Japan to rural Ontario, small observatories and amateur trackers were taking their usual nightly exposures of 3I Atlas. The object had become a fixture of the community since its discovery in July. Dozens of groups were contributing to open databases, stacking images, refining orbital elements, and comparing notes in real time. It was routine until it wasn't. One user on the Skytrack Discord noticed it first. Their coordinates didn't line up with NASA's predictions from the JPL Horizon system. The expected position placed 3I Atlas near a faint background star in the constellation Virgo, right ascension 14 hours, 8 meters 31 seconds, declination 6 degrees 22. But the live frame didn't match. The streak of light, dim but unmistakable, appeared almost a full arc minute ahead of that prediction. It was as if the comet had jumped forward. They assumed it was a timing error, maybe a clock offset or incorrect exposure log. But when other observers in Australia and Germany uploaded their frames hours later, the same discrepancy appeared. The same forward displacement. Independent systems, different hemispheres synchronized results. By the next morning, 10 separate observations confirmed that 3I Atlas wasn't where it was supposed to be. Normally this kind of error would vanish under statistical noise. Even large telescopes can suffer from tracking, drift, atmospheric turbulence, or calibration issues. But the magnitude of the offset made that explanation impossible. At its distance, roughly 24 astronomical units from Earth, a deviation of 1 arc minute translated to nearly 1 million kilometers of positional error. You don't get that from camera shake. You get that from physics changing direction. By sunrise in Europe, the first models started circulating. Some suggested outgassing jets of vapor nudging the path over time. Others proposed gravitational influence from Jupiter, though the alignment didn't fit. A third camp claimed it was an illusion caused by perspective, as Earth's orbit changed relative to the object's path. But those explanations fell apart. As the next night's data came in, the displacement wasn't static, it was growing. For every 12 hours of observation, 3I Atlas appeared to gain another 0.2 arc minutes ahead of prediction, a steady, consistent lead. Not a burst, not a flare, but controlled acceleration. What made this so unsettling was how clean the data looked. Normally, when comets accelerate due to gas jets, they brighten dramatically. Instead, the brightness curve of 3I Atlas dropped slightly from magnitude 148 to 151. It was moving faster but glowing fainter, as if something was adding energy without shedding mass. NASA's public site didn't comment. No press bulletins, no tweets, just silence. But behind the curtain, the JPL orbital tables quietly updated. Version 52 of the 3I Atlas dataset, uploaded 0314 UTC on October 24, revised the trajectory to match the new amateur coordinates. Acknowledging the shift without explaining it, within the community, the tone changed overnight. What began as a collaborative citizen science project turned into something anxious. Private chat groups started cross-checking exposure metadata, comparing calibration stars, calculating parallax corrections. They all reached the same uncomfortable conclusion: the data wasn't wrong. The coordinates really didn't match. If this were any other comet, the anomaly might have gone unnoticed for weeks. But 3I Atlas wasn't any other comet. Its interstellar origin meant every deviation mattered. Every fraction of a degree hinted at unknown forces at play. When you're tracking something that came from outside our solar system, gravity should be the only hand guiding it. So when gravity fails to explain its position, you're forced to ask the question no astronomer likes to ask. What else is steering it? And that's when the second image surfaced, one that turned quiet whispers of doubt into alarm. A faint structured glow around the nucleus captured by an amateur in Finland. The image that suggested 3I Atlas hadn't just moved, it had changed direction on purpose. N. The early days of interstellar tracking. Most breakthroughs came from institutions with billion-dollar budgets and instruments cooled to near absolute zero. But 3I Atlas changed that hierarchy overnight. It wasn't the deep space arrays or the orbiting observatories that first spotted the course shift. It was a network of citizen astronomers, working from rooftops, barns, and backyard domes. The story began with an innocuous upload to the Earth Exists database, a decentralized repository where amateurs share calibrated FITS files for public verification. One of the entries came from a small observatory near Turku, Finland. The image was dated October 23, taken with a 300mm Ritchie-Chrétien telescope and a cooled CMOS camera running a 60-second exposure. When the file was processed and plate solved, the centroid coordinates didn't align with NASA's orbital prediction. The offset was so consistent across multiple frames that it couldn't be dismissed as atmospheric noise. At first, most professionals ignored it. NASA's internal verification teams often receive hundreds of such submissions every week. Miscalibrated timestamps, faulty gain settings, or duplicated coordinates that don't pass statistical filters. But the Finnish team did something clever. They compared their stack with identical exposures from the Kiso Observatory in Japan and an independent group in Arizona. Despite differences in equipment and latitude, all three showed the same shift. 3I Atlas was leading its predicted position by just over 1 million kilometers. Still, there was no official comment, no alert circular, no data revision. For 4 days, the amateur network refined its findings in silence, assuming the professionals would soon catch up. But inside NASA, the data pipeline worked differently. The Jet Propulsion Laboratory's Horizon system, the gold standard for orbital predictions, only integrates new astrometric inputs from vetted observatories, listed in the Minor Planet Center's Certified Contributors list. Citizen stations, no matter how accurate, sit outside that gate. Their coordinates don't enter the official models until they're re-verified by credentialed astronomers. That procedural lag became critical. While the amateur network watched 3I Atlas drift further from its predicted path, NASA's published trajectory remained unchanged. The world's largest space agency was effectively operating on outdated information, unaware or unwilling to acknowledge that an interstellar object was no longer obeying its gravitational map. By October 26, the Earth Exists Collective compiled a 40-page analysis and sent it directly to the Planetary Defense Coordination Office. They included their raw images, calibration logs, and a full error budget. Within hours, their submission was quietly marked as received. No response followed. But then, at 0314 UTC on October 27, a new line appeared in JPL's orbital database. The object's right ascension and declination had been shifted, precisely matching the amateur data. There was no public explanation, only an updated timestamp. To the untrained eye, it looked like a routine update. To the amateur community, it felt like validation and proof that someone inside NASA had been watching their data the entire time. Yet the credit never came. No mention in the bulletin. No acknowledgement in the dataset footnotes. The correction was folded into the standard update cycle, as though the million-kilometer discrepancy had never existed. In the following days, frustration grew. Reddit threads and astrophotography forums filled with side-by-side comparisons of NASA's before and after plots. Commenters noticed that while the object's new path fit the amateur measurements, NASA's projection model left the residuals column blank, an omission that made the change harder to track statistically. It was a subtle move, the kind of bureaucratic silence that hides significance behind a wall of formatting. Then on October 28, a leak surfaced. A mid-level software engineer from one of NASA's contracted research partners anonymously confirmed what the amateurs had suspected. Internal simulations had already been adjusted days earlier, based on external data. The update delay was deliberate. An internal debate over whether to classify the anomaly as an instrumentation inconsistency or a physical deviation. That distinction mattered. Instrumentation inconsistency means human error, a harmless glitch. Physical deviation means a force not accounted for in current models, a real change in motion. By the time NASA finally synchronized its trajectory model publicly, the gap between amateur and institutional science had already closed, not because NASA caught up, but because they'd been forced to. In hindsight, this event marked a turning point. For the first time, open-source skywatchers had outperformed the largest space agency on Earth in both speed and transparency. Their data shared freely had caught what official channels initially overlooked, or perhaps what they preferred not to highlight. And buried in that overlooked data was a second pattern that no one had noticed yet. A faint but repeating colour anomaly in the object's coma, a green spectral arc that would later reappear in hundreds of independent frames. It would become the next mystery surrounding 3I Atlas, and raise a far harder question. If the amateurs were right about its position, what else might they be right about? In astronomy, precision is everything. When we predict the position of a celestial object, we're not talking about guesses. We're talking about coordinates that can land a spacecraft on a moving world. Millions of kilometers away, the mathematics of orbital mechanics are unforgiving, and the Jet Propulsion Laboratory's Horizon system is among the most accurate predictive engines humanity has ever built. Its models regularly guide interplanetary missions within meters of their targets. So when those same equations are suddenly wrong by over 1 million kilometers, it's not a rounding error. It's a crisis. The number first appeared in the logs of an amateur observer in New Zealand. He noticed that the difference between the predicted and observed coordinates of 3I Atlas translated at its distance from Earth to roughly 1 million kilometers of lateral deviation. That's about 3 times the distance between the Earth and the Moon. At first, no one wanted to believe it. Even gravitational perturbations from Jupiter, the solar system's heavyweight, wouldn't cause that scale of error in a matter of days. The raw math didn't make sense. To confirm the claim, researchers ran an independent simulation using the open-source OrbFit software. They input NASA's last known orbital elements, eccentricity, inclination, perihelion distance, and compared those to the updated position recorded by ground observers in Finland and Japan. The offset was real, consistent, and growing. The data wasn't an outlier, it was a trend. Here is what that number means in practice. When a comet approaches the Sun, it accelerates along a predictable curve determined by gravitational pull and radiation pressure. Even accounting for natural outgassing, small jets of vapor that can push the nucleus slightly, deviations rarely exceed a few hundred kilometers over months of observation. 1 million kilometers, by contrast, requires a net change in velocity of several kilometers per second. That's not a random jet of ice. That's thrust. Scientists calculated that to shift 3I Atlas by that much, within 48 hours, the equivalent of a sustained lateral force of about 10 to the power of 8 newtons would be needed, roughly the continuous thrust of multiple Saturn V rocket engines firing simultaneously. But nothing in nature produces a clean directional force like that without visible consequence. There were no flares, no sudden brightening, no photometric spike in the coma. The comet appeared eerily calm while somehow breaking Newton's expectations. A few conservative voices proposed that the anomaly could stem from ephemeris drift, the slow degradation of orbital predictions when the model lacks recent input data. But the last Horizons update had occurred less than 2 weeks before the deviation and new measurements were feeding in from observatories across the globe. The math simply didn't support that explanation. What unsettled many analysts wasn't just the displacement but the direction. When measurement errors occur, the object usually appears behind its predicted position because gravitational acceleration outpaces model assumptions. But 3I Atlas was ahead of schedule. It had somehow gained momentum. That single fact flipped the interpretation from measurement delay to energy injection. Something had added energy to its motion. If it was outgassing, it should have been bright. If it was gravitational, the pull had to come from an invisible source. If it was mechanical, well, that opened doors no one wanted to walk through. As the reports compiled, NASA quietly revised the orbital tables but didn't issue a clarification. The update metadata simply listed a calibration refinement. That sterile phrasing masked what was effectively an admission that the 1 million kilometer offset was now official. The professional silence only amplified speculation among independent astronomers and online physics forums. Some began comparing 3I Atlas anomaly to historical precedents. Oumuamua's unexplained acceleration in 2017, the way it deviated by a fraction of what 3I Atlas had now done. Harvey Loeb's earlier warnings resurfaced if interstellar objects were being propelled rather than pulled. The distinction between comet and probe might no longer hold. By October 27, the situation had evolved from academic curiosity to open anxiety. Tracking networks across Europe replotted their charts and found that the displacement wasn't just continuing, it was increasing exponentially, doubling roughly every 18 hours. The deeper implication became clear. For the deviation to persist, the force acting on 3I Atlas had to be sustained, not impulsive, as if an engine had ignited and then stabilized its burn. That was the night the numbers stopped feeling like data points and started feeling like intent. A 1 million kilometer error wasn't a mistake anymore. It was a message written not in words but in movement. In every known comet, jets follow the same rule. Heat makes ice vaporize vapor, escapes through fractures, and the resulting pressure pushes material away from the sundae. It's simple thermodynamics as predictable as steam rising from boiling water. But in late July 2025, images of 3I Atlas broke that rule completely. Instead of venting away from sunlight, the comet appeared to fire toward it. At first, most astronomers assumed they were seeing an optical illusion, a geometric trick caused by Earth's changing perspective. As we orbit the Sun, our angle relative to a comet's tail can make it look like the outflow points in impossible directions. But as more observatories captured the same pattern from vastly different latitudes, the illusion explanation collapsed. 3I Atlas wasn't being misinterpreted. It was truly emitting gas and dust against the Sun's radiation pressure, as if resisting it. That strange behavior lasted for nearly 6 weeks. The Hubble Space Telescope's July 21 imagery confirmed a bright forward-pointing plume, a so-called anti-tail glowing faint cyan made of ionized carbon and nickel compounds. But then, something changed. By early September, new frames from the Nordic Optical Telescope in the Canary Islands revealed that the jet had reversed direction entirely. The same nucleus that once appeared to push toward the Sun was now streaming material outward in the normal direction away from it. This phenomenon became known as the jet reversal mystery, and no one could explain it cleanly. In natural models, reversing a jet's direction requires either a total reorientation of the comet's rotation axis or a radical shift in the internal pressure of volatile gases. Both possibilities demand enormous energy, far more than sublimating ice can provide. Yet the reversal unfolded gradually over a few weeks as if the object were transitioning through a controlled sequence rather than a chaotic event. When researchers from the Keck Observatory ran a spectroscopic analysis of the emissions, they noticed another anomaly. The chemical signature had changed. Early emissions contained strong traces of carbon dioxide and cyanogen, both typical for outer system ices. After the reversal, the spectrum showed enhanced water vapor and metallic ions. That composition shift implied that deeper, hotter layers of the nucleus had suddenly become active. The transition happened almost precisely as the comet crossed the 3 AU mark, the distance from the Sun where sunlight begins to reach the threshold needed to melt internal water ice. Some scientists argued that the explanation was purely geochemical. Perhaps 3I Atlas had a layered composition, outer layers rich in carbon dioxide, inner layers dominated by water. As solar heating penetrated deeper, the active region migrated from one hemisphere to another, naturally flipping the jet orientation. But the physics didn't quite add up. The reversal wasn't random. It aligned almost perfectly with the object's approach to perihelion, the point of maximum solar energy. The timing looked engineered. That was when Avi Loeb's team at Harvard released a paper suggesting that if the forward-facing jet had acted as a deceleration burn, the new anti-solar emission could represent acceleration, the kind of paired maneuver a spacecraft might use to adjust course around a gravitational body. Loeb's phrasing was cautious, a controlled inversion consistent with a deliberate trajectory correction, but the implication was hard to ignore. NASA meanwhile avoided comment. Internal logs showed that its solar observatories had captured overlapping frames during the reversal window, but those images were never released. The official stance was that data quality near solar conjunction is insufficient for public analysis. For independent researchers, that sounded less like caution and more like containment. Back in the amateur community, the reversal became visible even through mid-range backyard telescopes. Photographers in Argentina and Poland independently recorded time-lapse sequences, showing the plume's gradual rotation, its brightness fluctuating in rhythmic intervals 17 minutes apart. That periodic pulsing couldn't be explained by sunlight or rotation alone. Something was modulating the outflow. To visualize the event, imagine a slow pivot of thrust. The jet doesn't flick on and off like a valve. It turns arcs and steadies in its new orientation. The dust trail follows, forming a faint S-curve across the background stars. For a natural comet, that kind of elegant symmetry is rare. For a guided system, it's expected. By the end of September, the jet reversal mystery had become more than a curiosity. It was the cornerstone of a growing argument that 3I Atlas might not be behaving on its own. And when those new trajectories were projected forward into October, they predicted something no one wanted to believe. If the reversal continued at its measured rate, 3I Atlas would intersect a path dangerously close to Mars' orbital plane just days before perihelion. Whatever had caused the reversal wasn't finished yet. It had simply turned to face its next destination. When comets approach the Sun, they put on a show. Solar radiation heats the nucleus. Volatile ices sublimate and jets of vapor push dust into space, forming the glowing coma and tail that make them visible to us. The closer they get, the brighter they burn. It's one of the most predictable relationships in astronomy. Proximity equals luminosity. But in late October 2025, as 3I Atlas moved toward perihelion, it did the opposite. It dimmed, by every known physical law that shouldn't have happened. The Jet Propulsion Laboratory's brightness forecast had predicted a steady rise in magnitude from 148 to 132. As the comet approached the Sunday, instead, amateur telescopes and professional photometers recorded the reverse trend, a faint, consistent decline to magnitude 151. That's a 25 to 30% reduction in luminosity during a period when sunlight exposure had tripled. The readings weren't noise or calibration errors. They were cross-verified by observatories in Chile, Spain, and South Korea. The object was unmistakably fading while heating up. At first, researchers assumed that the dimming was caused by a loss of reflective dust, that perhaps the jets had ceased ejecting large grains, leaving a thinner, more transparent coma. But spectra told a different story. The comet was still releasing roughly 25 kilograms of water per second, confirmed by the James Webb Space Telescope's mid-infrared readings. In other words, activity was still strong. The gas production hadn't decreased. The light simply wasn't escaping. One possible explanation was geometry. Maybe the bright side of 3I Atlas had rotated out of view, and we were seeing its darker hemisphere. But the object's rotation period, measured through flickering photometric variations, was roughly 9 hours. Over the course of several nights, that rotation should have averaged out any surface lighting bias. Yet the brightness curve continued to trend downward, with almost mathematical precision. That's when independent researcher David Sereda compared frames from NASA's LASCO C3 coronagraph, a telescope that blocks the sun's glare to photograph nearby space. In those images, the object's coma didn't appear weaker. It appeared denser. Light wasn't decreasing because less was being produced, it was decreasing because more was being absorbed. Sereda proposed that the comet might have formed a transient plasma shell, a magnetic sheath trapping charged particles around the nucleus. This kind of self-contained cloud could scatter or refract incoming light in ways that make the object appear fainter from Earth. Plasma behavior near the Sun is notoriously difficult to model, but the spectral evidence supported his theory. A new emission line corresponding to ionized nickel appeared in the data, suggesting that metal atoms were being excited and confined in a structured magnetic field. The effect would be similar to fog around a street lamp. The lamp doesn't go dark, its light just doesn't reach you clearly. For 3I Atlas, the fog was magnetic, an electromagnetic cocoon surrounding the object as it encountered the solar wind. But some analysts pushed the idea further. They noted that the dimming coincided precisely with the onset of the course deviation reported by amateur astronomers. The moment the object appeared to accelerate, its brightness fell. That correlation implied a shared cause energy being diverted away from visible light into another form. If the object was somehow storing or channeling energy even naturally, it could explain both anomalies at once. Instead of radiating sunlight through dust, it was absorbing or redirecting it. In a natural comet that would require dense metallic material acting as a conductor. In a technological object, it might suggest something else entirely. Deliberate energy management. NASA's official stance was non-committal. The agency cited variability in photometric geometry, an incomplete phase angle correction bureaucratic language, meaning they didn't know. But in private communication, logs leaked from a European research consortium. One phrase appeared repeatedly in discussions about the anomaly active albedo suppression, a fancy way of saying the object might be dimming itself. Why would something do that? One answer is simple temperature control. Reflectivity determines heating. By reducing its brightness, 3I Atlas could lower surface absorption and prevent volatile layers from disintegrating too fast near the Sunday. That's not just survival instinct. That's design logic. By the final week before perihelion, the dimming reached its lowest point, plateauing at magnitude 153, before the object disappeared behind solar glare. For astronomers, it was an anticlimax, the most energetic phase of its journey hidden from view. But for the theorists watching the light curve flatten into silence, the message was chilling. Comets brighten when they're dying. 3I Atlas dimmed when it was alive. In the void between stars, plasma is chaos. It swirls fractures and dances along magnetic lines like invisible lightning, unpredictable and wild. But what astronomers began to see around 3I Atlas in late October 2025 wasn't chaos. It was structure. The discovery came accidentally. On October 24, the Earth Exists network uploaded enhanced composites from multiple amateur observatories across northern Europe. The observers had applied nothing exotic, just linear contrast stretching to highlight faint emissions. What appeared on their screens stopped them cold. The faint bluish glow around 3I Atlas wasn't a smooth halo. It was segmented, patterned. Radial spokes of light extended from the core like the arms of a gear, evenly spaced, symmetrical, rotating slightly between exposures taken minutes apart. One analyst counted 8 distinct bands forming a circular lattice, each with measurable persistence over several frames. To the naked eye, it looked artificial, like a plasma containment field in motion. When NASA's LASCO C3 coronagraph images were cross-referenced, the same faint geometry emerged. 4 exposures taken over 6 hours showed a repeating pattern that flickered between green and magenta wavelengths. The correlation wasn't pixel noise. It aligned across independent instruments using different detectors in different orbits. That's when people began whispering about the plasma grid. Physically, there's only one way to explain such structure. A coherent magnetic field organizing charged particles around the nucleus. Natural comets can generate weak magnetospheres when ionized gas interacts with the solar wind, but those fields are unstable, turbulent, irregular, transient. What surrounded 3I Atlas looked organized, almost engineered. Spectroscopic data deepened the puzzle. The Keck Observatory's readings showed emission peaks corresponding to ionized nickel, cyanogen, and hydrogen plasma. 3 elements, with sharply different excitation energies. In a typical comet, these emissions would mix randomly in the coma, blurring into a uniform glow. Around 3I Atlas, they appeared stratified, separated into distinct zones. The green emissions formed the outer ring. The blue clustered near the core, and a thin pink filament traced the inner boundary. It was a plasma rainbow arranged with uncanny precision. Theorists scrambled to model it. Could a rotating magnetic core, perhaps due to the object's spin, create such symmetry? Possibly if the nucleus contained ferromagnetic materials. But interstellar comets are mostly ice and carbon. For a magnetic field to maintain that degree of order, something would need to generate it continuously like a dynamo. NASA's official statement labeled the observed geometry processing artifacts, but when European Space Agency scientists tried replicating the images, the patterns persisted, even in raw, uncompressed data. The probability of 8 symmetrical plasma arms forming through random outgassing was effectively 0. One independent researcher, Dr. Meera Chowdhury, of the Indian Institute of Astrophysics, proposed a bold alternative. She suggested that the field wasn't random plasma at all, but a magnetically aligned dust sheath stabilized by electric currents induced as the object crossed the solar wind. In her words, if 3I Atlas carries conductive material, even metallic veins beneath its crust, then its motion through charged plasma could create localized magnetic feedback loops. What we're seeing might be the visual signature of a self-regulating electromagnetic boundary. That hypothesis might sound mundane, but it carried profound implications. A self-regulating boundary means the object wasn't merely reacting to solar energy. It was managing it. Meanwhile, on online forums, image analysts discovered rhythmic flickering in the plasma bands, a modulation occurring every 119 seconds. Some dismissed it as cosmic ray interference. Others pointed out that cosmic rays don't pulse. This was periodic, consistent, and localized to the same region of the coma. If true, it suggested some kind of cyclical discharge, like a controlled current flow. NASA didn't confirm or deny the periodicity. Their silence only amplified the mystery. As more frames came in, the plasma geometry appeared to evolve, the outer ring contracting while the inner glow brightened. Amateur astronomers described it as breathing. The nickname stuck the breathing field. In natural physics, plasma obeys chaos. In 3I Atlas, it obeyed pattern, and in the calm between images, it seemed to pulse with intent, as if something deep within the object was balancing forces we still don't understand. By the time it slipped behind the sun days later, the structured glow had vanished from view. But the data, the geometry, the frequencies, the rhythm remained archived in hundreds of files across the world. Patterns that no comet should ever make. Patterns that might one day prove they weren't random at all. It was a cloudless night over Turku, Finland. On October 25th, 2025, the kind of crystalline Arctic evening when the air feels carved from glass. Temperatures had dropped below freezing, and the amateur observatory known locally as Aurora Station 9 was tracking 3I Atlas on its routine schedule. Nothing unusual was expected, but as the telescope sensor captured its 10th exposure of the night, the operator, a retired engineer named Kari Aaltonen, noticed something his calibration software couldn't explain. A curved green filament stretching across the field of view, faint yet distinct like an aurora frozen in space. At first, he assumed it was an imaging artifact, maybe light from the northern horizon leaking into the sensor. But the arc wasn't aligned with Earth's sky. It was anchored to 3I Atlas itself. The curve emerged from the object's coma, sweeping outward in a perfect semicircle. Before fading into the black, Kari checked the orientation twice. The feature wasn't parallel to the sun's direction. It was perpendicular, a ring of light where no comet should have one. He uploaded the raw FITS file to the Earth Exists network at 0117 UTC. Within hours, other astronomers across Europe began analysing it. The green glow wasn't local interference, it was real. Observers in Germany, Poland and Denmark replicated it the next night using different equipment, different filters and different tracking software. The arc appeared each time faint, but consistent, and always connected to 3I Atlas. Spectroscopic analysis confirmed that the emission line corresponded to ionized nickel and diatomic carbon glowing at approximately 511 nanometers, the same wavelength that gives comets their characteristic teal hue. But there was a difference: this arc wasn't diffuse like normal comet tails. It was razor-sharp, confined to a band less than 0.1 arc-minutes thick, stable across multiple exposures. That precision suggested magnetic confinement, a thin plasma sheet guided by an organized field. NASA's public channels didn't mention the event, but internal chatter on the Minor Planet mailing list hinted that the anomaly had reached official eyes. One contributor referenced unexplained emission asymmetry north of the nucleus, the bureaucratic shorthand for "we saw it too." Yet no images appeared on NASA's servers, only placeholders labelled pending verification. Meanwhile, Kari continued documenting the arc night after night. On October 27, the feature brightened, dramatically visible, even in unfiltered monochrome exposures. What stunned analysts was its shape. The arc now curved back toward the nucleus, forming a faint horseshoe, as if the plasma field were folding in on itself. Astrophysicist Dr. Meera Chowdhury, who had already analysed 3I Atlas plasma geometry, proposed a daring theory. She argued that the arc might represent magnetic reconnection, a process where twisted magnetic field lines snap and realign, releasing enormous amounts of energy. This phenomenon happens frequently in the sun's corona, powering solar flares, but it had never been observed so cleanly around a comet-like object. To generate a visible green arc through reconnection 3, I-Atlas would need a localized magnetic field thousands of times stronger than anything measured on natural bodies of similar size. That strength implied internal conductivity, metals, currents, or something capable of sustaining electromagnetic tension. The Finnish arc quickly became a sensation in online astronomy communities. Reddit threads exploded with enhanced images, some comparing the feature to plasma toroids seen in fusion experiments. Others speculated it was a kind of shield, a boundary between the object's internal field and the solar wind. One striking comparison circulated widely: the magnetopause of Earth, captured by the Themis spacecraft, and Kari's photo of the green arc. The shapes were nearly identical. By the time larger observatories turned their attention to the phenomenon, the opportunity was gone. On October 29, 3I Atlas entered solar conjunction, vanishing into the glare. Kari's last frame, captured just 17 minutes before the object disappeared, showed the arc breaking apart into discrete luminous knots drifting away like beads on a string. To this day, no institutional observatory has released corroborating imagery. The only clear record remains the Finnish data: 32 raw exposures, showing a coherent, curved emission detached from the nucleus of an interstellar object. For Kari, it was the moment of a lifetime. An unintentional discovery that might redefine what we call a comet. For the rest of the world, it became something else entirely. The first visual hint that 3I Atlas might not just react to the solar wind, but shape it. And as the green arc faded into the sun's glare, so too did the illusion of understanding. The heavens were no longer behaving like a passive system. Something out there was writing its own geometry, and Earth had caught it frame by frame from a cold Finnish sky. When 3I Atlas made its close approach to Mars on October 3, 2025, every major space agency had a front row seat. The object's trajectory carried it within 22 million kilometers of the red planet, close enough for high-resolution cameras aboard NASA's Mars Reconnaissance Orbiter, MRO, and ESA's Trace Gas Orbiter, TGO, to capture unprecedented data. Those instruments can resolve details down to tens of kilometers per pixel, enough to detect a comet's coma structure, dust plume, or even fragmented ejecta. It should have been the best observation window in human history for an interstellar object. Instead, it turned into a blank spot. For weeks, no images were released. Both NASA and ESA's mission dashboards showed data acquisition complete messages for that date, yet the corresponding imagery never appeared in their public archives. Normally, raw files from MROs, HiRISE and CTX cameras are uploaded within days. This time, the status pages listed an unfamiliar phrase pending quality verification. That delay, now stretching beyond 3 weeks, immediately drew suspicion. Amateur astronomers who had been coordinating with the agencies to time their ground-based observations were stunned. They had expected a quick turnaround. Some had even synchronized their telescopes with MRO's orbit to capture simultaneous frames from Earth, Mars and space. A triangulation experiment designed to produce the first true 3D parallax model of an interstellar object. But when they compared timestamps, they found gaps in the official record, entire segments of orbital passes missing, as if someone had cut frames from a reel. The missing data covered a crucial 5-hour window exactly when 3I Atlas passed behind Mars from Earth's perspective, shielded from direct observation. It was the perfect opportunity for high-resolution imaging free from solar interference. The absence of those frames felt almost deliberate. NASA's official explanation cited communication prioritization during solar conjunction, suggesting that bandwidth constraints forced engineers to downlink critical Mars surface data instead. But internal transmission logs leaked days later by a former subcontractor told a different story. The orbiter's telemetry clearly showed active imaging commands executed during the missing window, with exposure lengths and angles matching the predicted position of 3I Atlas. The cameras had indeed fired. The data simply never reached the public servers. The European Space Agency remained equally quiet. Their CASSIS camera on the ExoMars Trace Gas Orbiter was also scheduled to observe 3I Atlas during its Mars flyby. Yet ESA's press release merely stated no usable data due to solar interference. A week later, an internal memo leaked from ESA's Planetary Science Division confirmed that frames were captured, but flagged as anomalous during automated analysis. The note contained a cryptic line: radiometric consistency fails standard calibration signal pattern not characteristic of dust or gas. No one outside the agencies has ever seen those frames. Speculation spread quickly. Some scientists theorized that the images revealed plasma interactions between 3I Atlas and Mars, a thin atmosphere, perhaps electromagnetic disturbances or unexpected ion trails. Others believed the cameras had caught a structural silhouette, something solid within the coma that didn't resemble a natural nucleus. Adding weight to the rumors, an independent researcher named Dr. Miguel Aranda, who had worked on HiRISE's optical calibration team, published an unsigned note online describing a linear symmetry in the preliminary images he'd glimpsed before, the data lockout. According to Aranda, the object's brightness profile contained 2 distinct peaks, as if the nucleus had separate reflective zones spaced evenly apart. A binary structure, not a single tumbling rock. NASA quickly denied Aranda's account and issued a statement claiming no irregularities detected in mission imaging. But their denial came with an odd footnote, a formal reminder that all staff must adhere to ITAR data handling protocols, a classification clause usually reserved for defense-related material. To outsiders, it looked like overkill for a simple comet picture. Meanwhile, the Mars atmospheric and volatile evolution, MAVEN Orbiter's instruments detected something peculiar during the same time window, a brief spike in charged particle density around Mars magnetotail. It lasted only 6 minutes, too short for a solar event, but perfectly aligned with 3I Atlas passage through the region. The data hinted at an interaction between the object's field and Mars atmosphere, as if the interstellar visitor had brushed against the planet's magnetic envelope and left a measurable trace. Officially, NASA called it a coincidental plasma anomaly. Unofficially, it was the last verified signal anyone received from Mars before the period of unexplained radio silence that followed. By the time communications resumed, the data stream was back to normal, neat, complete, and missing the one sequence that mattered most. To this day, the HiRISE images from October 3rd remain unreleased. The public archive jumps seamlessly from October 2nd to October 4th, leaving a hole precisely where 3I Atlas crossed Mars orbit. A hole shaped like a mission or intent. Whatever those missing frames showed, someone decided the world wasn't ready to see them. To understand how this story spread, we have to look at a strange gap that appeared not in the sky but in the data pipeline itself. The LASCO C3 coronagraph aboard the SOHO spacecraft has been taking continuous images of the Sun and surrounding space for nearly 3 decades, one frame every 12 minutes. Its archive is a near-perfect record of everything that passes near the solar disk. But on the 29th of October 2025, as 3I Atlas reached its closest approach, the sequence broke. Between 0412 and 0836 UTC, no images were recorded. A 4-hour void. To casual viewers, that might seem trivial, but for scientists who rely on that data stream, it was unprecedented. Even during spacecraft resets or telemetry dropouts, partial frames usually survive. This time the gap was absolute, and it happened during the single window when 3I Atlas would have been fully visible inside the C3S field of view. When the feed resumed, the object was gone. In its place, a faint residual flare lingered for several frames before dissipating. NASA released no statement. The official archive simply labeled the interval as data unavailable. Independent analysts immediately noticed something else. The surrounding telemetry showed no signs of system error. The coronagraph was functioning perfectly. Temperature, voltages, orientation, all nominal. The spacecraft didn't fail. The data was deliberately excluded. Some suspected simple censorship. Perhaps NASA wanted to remove overexposed frames that might confuse the public. But the missing block included not just imagery but corresponding magnetometer and solar wind data. The instruments that measure charged particles around the Sunday, that combination suggested something else. That the event captured during that window wasn't photometric at all, it was energetic. When the sequence resumed, observers noted a faint asymmetric haze on the western edge of the field, a subtle distortion as if light were bending around an invisible mass. Gravitational lensing on such a small scale was impossible unless the object had passed close enough to warp the solar wind magnetically. That distortion lasted for nearly 40 minutes. ESA scientists privately circulated a memo acknowledging the anomaly. One excerpt leaked days later localized refractive event near perihelion, not solar in origin. It was the only semi-official acknowledgement that something had occurred during the blind window. Later frame analysis by independent teams revealed pixel-level traces, residual imprints left by the missing images. Each missing frame still left a checksum, a digital signature indicating the volume of data removed. The checksums varied cyclically, suggesting that the deleted sequence contained frames of differing brightness. In other words, something was changing rapidly. From shot to shot, too bright for comfort. What could outshine the sun at that proximity without being destroyed? That's the question no one at NASA will answer. Theories range from electromagnetic discharge to artificial shielding to directed reflection of sunlight through plasma focusing. Whatever it was, it left an unmistakable imprint on the timeline, a deliberate erasure right at the moment of maximum curiosity. The event became known as the LASCO gap. For months after its discovery, enthusiasts tried to reconstruct the missing segment using interpolation from earlier and later frames. Their reconstructions showed a faint moving glow forming a loop before vanishing, consistent with the trajectory that 3I Atlas was predicted to follow. If true, it would mean the object executed a controlled curve around the sun rather than a chaotic sling-by, a maneuver that defies everything natural comets do. The only official note added to NASA's database afterward was solution reference 53 updated Oct2 70314 UTC later, quietly deleted without comment. Whatever was hidden in that missing data remains buried beneath bureaucratic silence and checksum residue. It would not be the last silence, because in the days following the LASCO gap, a new set of orbital maps began to appear, this time on NASA's own public site. The coordinates for 3I Atlas suddenly changed again, not dramatically, just enough to matter. Its post-perihelion path now bent subtly northward, instead of continuing its projected curve. The difference, less than 1/10 of a degree, might seem negligible, but at interplanetary scale that translates to millions of kilometers of deflection. No announcement accompanied the change. The orbit tables were simply overwritten. Version 54 replaced 53 without explanation. But for those who had been watching from the beginning, the pattern was unmistakable. Each time 3I Atlas behaved in a way the models couldn't explain, the official data quietly adjusted afterward to erase the anomaly. When gravity fails, math becomes storytelling, and this story was being rewritten in real time. By early November, Amateur astronomers had already recalculated their own trajectory using the latest available coordinates. The new path intersected nothing known, not the asteroid belt, not Mars orbit, not any major gravitational resonance point. It was as if 3I Atlas was heading toward a blank coordinate, a region of deep space with no predicted perturbations. That blankness became the new obsession, because if an interstellar object deliberately corrected course to head somewhere specific, that somewhere had to matter. What lay ahead was empty space, but perhaps not for long. When an object escapes the gravity of the Sun, its velocity and trajectory are governed by a single set of immutable laws. But what happened after the LASCO gap violated every one of them? Orbital reconstruction based on the latest amateur data suggested that 3I Atlas did not continue along a standard hyperbolic exit curve. Instead, its outbound path showed a slow lateral drift as if it was sliding sideways through space. To visualize it, imagine a marble rolling down a funnel, then curving not outwards but tangentially across the rim, defying the funnel's shape altogether. That's what the new trajectory maps showed. No known natural process could account for that motion. Gravitational perturbations from the planets were too weak, solar pressure too constant, and there were no nearby bodies capable of producing such torque. Yet the deflection was real, measurable through parallax, even in amateur images. The revision first appeared quietly in NASA's Small Body Database on November 2, 2025. Within hours, sharp-eyed astronomers noticed that the official orbital inclination had shifted by 0.14 degrees small in print, enormous in physics. That meant the object was now on a new plane entirely, one that no gravitational model predicted. By cross-referencing the old and new data tables, analysts found that the change originated from just 4 new measurements, all attributed to an internal observatory code never before seen in the database. The source field simply read DSN, the Deep Space Network. The Deep Space Network consists of 3 massive radio antenna complexes positioned in California, Spain, and Australia. Primarily used to communicate with spacecraft beyond Earth's orbit, it does not track comets. Yet, according to the metadata, those 4 entries were radio astrometric fixes, meaning radar echoes rather than optical images. That detail baffled scientists. No radar system had ever successfully bounced a signal off an interstellar object at such a distance. The Goldstone antenna can detect large asteroids within a few million kilometers, but 3I Atlas was over 150 million kilometers away at the time. A return signal under those conditions should have been impossible, unless the target was actively reflecting. Within days, rumors spread that Goldstone had indeed attempted an experiment. A deep frequency pulse meant to map the comet's nucleus. The pulse was sent. Something answered. The reply wasn't strong, just a faint echo, lasting 0.8 seconds, enough to generate a distance fix and update NASA's trajectory tables. But the waveform analysis leaked, later revealed something impossible. The echo contained secondary harmonics, repeating peaks at uniform intervals. A natural rock scatters radar chaotically. This pattern looked structured. Goldstone's engineers never confirmed the leak. Officially, the experiment was cancelled due to low signal-to-noise ratio. But those 4 mysterious data points labelled DSN remain in the record, the only radar observations ever logged for an interstellar object. The existence of those harmonics triggered a quiet frenzy among SETI researchers. For years, the search for extraterrestrial intelligence had operated on the assumption that any signal would come as deliberate transmission, not as reflected radar. But this changed the paradigm. If 3I Atlas was capable of modulated reflection, it could act as a passive responder, a cosmic mirror designed to return structured echoes when pinged. SETI analysts ran the data through their standard filters used for narrowband detection. What they found made headlines in the quietest way possible. They found timing. The spacing between the harmonic peaks was 137 seconds, precisely matching the object's rotational period as inferred from optical light curves. The reflection wasn't random. It was synchronized with its spin. For radiophysicists, that detail was staggering. It meant that whatever caused the radar reflection was locked to the object's rotation like a beacon turning with the body. Either the radar pulse had resonated with internal cavities, or 3I Atlas was built to respond that way. SETI quickly issued a statement downplaying the findings as coincidental harmonic interference. But in internal memos later leaked to journalists, one phrase stood out: timing coincidence, statistically implausible under random scattering. After that line, the trail went dark. No further radar experiments were reported. Goldstone's logs for that night were sealed for maintenance. The small window during which an interstellar object had literally echoed back closed as quietly as it had opened. Yet within those 4 faint data points lay the final confirmation that the story of 3I Atlas was no longer about chance or error. It was about dialogue, even if one side refused to admit it. In the aftermath of the Goldstone event, official communication from NASA and ESA grew noticeably restrained. Press releases that once detailed every nuance of the interstellar visitor shifted into vague summaries about ongoing analysis and data review. The live orbit tracker that once updated hourly now refreshed only once every 24 hours, and each update pushed 3I Atlas a little further from where the amateurs had last measured it. But while the agencies went silent, the sky did not. On November 8, 2025, a small observatory in Arizona called Copper Ridge detected a faint moving object near the position where 3I Atlas should have been post-perihelion. At first, the team assumed it was background noise. The magnitude was nearly 162, almost at the limit of detection. But stacking multiple exposures revealed a consistent drift, matching the expected velocity of the missing interstellar object. When they compared it to NASA's latest trajectory, it fit perfectly, but with one crucial difference. The object was farther from the Sun than predicted by nearly 0.5 astronomical units, meaning it had decelerated. That finding made no sense. Objects leaving the solar system don't slow down, they speed up slightly as radiation pressure continues to push them outward. Yet 3I Atlas was doing the reverse, as if some unseen drag were holding it back. For weeks, more observations confirmed the trend. Each new data point placed the object slightly behind its predicted position, the exact opposite of the acceleration that had caused the first anomaly back in October. It was as though the engine that once pushed it forward had now switched into reverse. Amateur astronomers joked grimly about it turning around, but the math was uncomfortably close to that idea. If the deceleration continued at its measured rate, 3I Atlas would reach a full stop relative to the Sun within 18 months. In celestial mechanics, that is equivalent to defying gravity. Some analysts proposed that solar radiation pressure had changed due to seasonal variation in the Sun's output. But the Sun doesn't dim or brighten that much over such short timescales. Others argued that the object might be venting material in the opposite direction, creating a braking force. But the photometric data showed no significant increase in outgassing. The coma remained faint, stable, and symmetrical. By mid-November, the community was split. Half believed the deceleration was a measurement illusion caused by calibration drift in small telescopes. The other half saw it as the second act of the same mystery, a deliberate course correction, reversing the earlier acceleration. In early December, a group of astrophysicists from the Max Planck Institute attempted a full orbital reconstruction using every available observation, amateur and professional. Their model revealed a subtle oscillation in the object's path, small deviations back and forth along its trajectory line, like a sine wave. That wobble couldn't be produced by gravity or outgassing alone. It required a periodic lateral force, something firing in bursts. The pattern repeated every 92 hours, precisely 4 times per spin cycle. It was as if 3I Atlas was breathing again, but this time in motion. That rhythmic drift brought back memories of the earlier plasma pulses detected during the jet reversal phase. Some theorists wondered if the two phenomena were connected, the same underlying mechanism manifesting in different environments, one near the Sun, the other in deep space. NASA refused to comment on the oscillation data, but on December 2nd, a curious update appeared on the JPL database. A single line of text added to the object summary: post-perihelion trajectory re-evaluation pending additional DSN data. It was the first time the Deep Space Network had been mentioned publicly in connection to 3I Atlas. Then the line vanished 2 days later. Meanwhile, the amateurs kept tracking. Their new coordinates revealed something that most professionals ignored: the faint reappearance of the same green hue first seen in Finland weeks earlier. Even though the object was now far beyond the orbit of Mars, its coma glowed faintly teal. Too bright for its distance, too cold for simple chemistry. That spectral signature suggested ongoing excitation, as if residual current still flowed through its plasma sheath. In a final series of exposures captured on December 9th, the glow pulsed once every 9 minutes before fading completely from visible detection. The object was gone, at least optically, but radio receivers in Australia recorded a brief anomaly. That same night, a transient signal at 856 MHz, lasting just under 2 seconds. It came from the direction of 3I Atlas predicted coordinates. The signal wasn't strong enough to decode just a soft rise and fall like static under a whisper. Then, silence. For the first time since its discovery, there were no confirmed detections of 3I Atlas anywhere in the sky. No optical trace, no radar echo, nothing. It had slipped away as quietly as it arrived, leaving behind a trail of contradictions no telescope could resolve. Astronomy thrives on closure, every anomaly demands an answer. But 3I Atlas defied that instinct. Each explanation outgassing gravity plasma data error only opened more questions. And somewhere beyond Mars in the cold expanse where sunlight fades into black, the object kept its own counsel. The amateurs archived their files and moved on to new targets. NASA closed its updates. The public forgot, but for those who had seen the data firsthand, the silence that followed was louder than any discovery. Because sometimes what vanishes speaks the most. For weeks after the final sighting of 3I Atlas, every observatory and radar array on Earth pointed sensors toward its last known coordinates. Nothing came back. It was as if the object had dissolved into space itself. Then, on December 15th, a faint detection appeared from an unexpected source, the Goldstone Solar System radar. During a routine calibration run, aimed at the asteroid 2001, FO32 engineers noticed a tiny residual echo offset by 003 degrees from the target. When they triangulated the signal, it matched the projected outbound path of 3I Atlas. The echo was weak, irregular, and lasted only 11 seconds, but within it were patterns identical to the earlier harmonics seen in the October experiment. 3 peaks evenly spaced, each separated by exactly 137 seconds, the same rotational timing that had baffled scientists months earlier. At first they dismissed it as data contamination from previous experiments, but when the next night's calibration run produced the same faint echo again, the coincidence became impossible to ignore. Something was still there. Goldstone's data logs show that the echo repeated intermittently for 5 nights before vanishing completely on December 20th. The amplitude decreased each time as if the source were receding or its reflective surface dimming. By the final detection, the return strength had dropped below background noise. That pattern of fading was consistent with one thing: an object moving steadily away from the sun under its own controlled deceleration. The trajectory extrapolated from the echoes pointed toward interstellar space, but not along a random escape vector. It aimed roughly toward the constellation Ophiuchus, a region containing no major stellar systems within the next 20 light-years. Just emptiness. NASA never published the data, but internal documents later obtained through the Freedom of Information Act confirmed the radar detections and even listed them under a classified appendix labeled Anomalous Signal Return Non-Asteroidal. The files remain redacted. When journalists pressed for clarification, a spokesperson replied only that Goldstone's data may reflect unverified interference from unrelated sources. Yet the agency quietly revised 3I Atlas orbital elements one last time, pushing its estimated position slightly northward, consistent with the radar direction. After that, there were no more updates. The object passed beyond the reach of human instruments, leaving nothing but memory, speculation, and silence. But in that silence, some found meaning. SETI researchers began revisiting old assumptions about how first contact might occur, perhaps not through obvious broadcasts or alien megastructures, but through subtler forms of communication. Objects that move against gravity, signals that echo when called, trajectories that change without force. Maybe what passed through our system wasn't a message at all, but a question. In the final days of December, the amateur astronomers who had first tracked 3I Atlas gathered online for one last session. They compared their files, their timestamps, their sleepless nights spent watching a faint streak of light behave like nothing else in the sky. What united them wasn't certainty, it was wonder. For a moment, humanity had glimpsed something that didn't fit the rules, and in that dissonance found awe. NASA closed its official report with the standard phrasing object no longer observable trajectory consistent with outbound interstellar vector. A neat ending to an untidy mystery, but for those who saw the data before the edits, before the deletions, before the gaps, the story will never end. Because somewhere out there, beyond the reach of our telescopes, something that once answered our radar pulses drifts silently between the stars, and if it ever decides to turn back, we may not be ready to ask again. When scientists reviewed the entire sequence of observations months later, one pattern stood out. Silence always followed noise. Each burst of data, each anomaly, each leak was met by an equal and opposite reaction of omission, as if an invisible editor were trimming the record frame by frame to maintain equilibrium. The discovery logs showed this symmetry in chilling precision. When the amateurs announced the first deviation, NASA's database paused updates for 48 hours. When the Finnish arc surfaced, the agency pushed a software patch to its public archives, restructuring file indexes. When the LASCO gap occurred, telemetry was rerouted through a redundant satellite, and when the radar harmonics leaked, the DSN servers underwent scheduled maintenance. Every revelation produced silence. Every signal was followed by erasure. To many this looked like damage control, but to some theorists it suggested something stranger feedback. If 3i Atlas was responding to observation, adjusting its output to attention, then the silences were part of the conversation. It would mean that the object didn't simply move through space, it moved through awareness. It reacted not only to light but to being watched. That idea, once dismissed as pseudoscience, found unexpected support in data from unrelated missions. During the weeks when 3i Atlas was brightest, the Mars Atmosphere and Volatile Evolution mission reported higher than normal radio static in the X-band, an interference pattern similar to what deep space antennas experience when tracking. Variable sources. When the object dimmed, those spikes vanished. If correlation implies causation, the timing aligned too perfectly to ignore. In classical mechanics, observation doesn't alter motion, but in quantum physics it can. The act of measuring a particle collapses its probability wave into a fixed state. What if a similar principle scaled upwards somehow? Not through physics, but through interaction awareness itself affecting behavior. The hypothesis remained untestable, but haunting, because if true, the object that we had been watching might have been watching back. One footnote buried in the Jet Propulsion Laboratory's internal correspondence added an eerie layer to that thought. It mentioned a sudden shift in the object's apparent brightness, coinciding with the moment one of NASA's ground stations in Madrid began transmitting radar pulses. The document described it clinically reflectivity alteration, possibly correlated with uplink initiation, but that line implied something extraordinary response time. The delay between transmission and change was exactly what you would expect if the object had detected the signal, processed it, and reacted. It was short enough to rule out coincidence, long enough to suggest deliberation. No one ever published those numbers. They exist only as redacted timestamps in a file marked internal calibration discrepancy. To the general public, 3i Atlas remained a curiosity, a frozen rock with a strange orbit and a vanishing act. But within the small circles of astrophysicists, engineers, and data analysts who handled the raw information, the tone changed. They stopped calling it a comet. They started calling it an event. The difference is subtle but profound. A comet is an object. An event is something that happens. Events have intention. They begin, end, and sometimes repeat. And as 2026 approached, the night sky returned to silence. But a few radio telescopes kept their dishes aimed toward the coordinates where 3i Atlas should have been. Not because they expected a reply, but because once you've heard something answer, you can't stop listening. In February 2026, a quiet update appeared on an obscure European Space Agency server, a recalibration notice for the Solar and Heliospheric Observatories archive. Buried within it was a single line referring to frameset C310427, recovered from partial telemetry. For months, researchers had assumed those files captured during the LASCO gap were permanently lost. Now they were listed as restored, though not released. No announcement was made. No images accompanied the notice. But the metadata revealed one tantalizing clue. The exposure times for those frames were double the usual value, 24 seconds instead of 12. That implied manual adjustment. Someone had deliberately extended the capture duration during the anomaly window. The timing matched perfectly with the moment 3i Atlas would have been nearest to the Sunday. Someone on board had tried to see more. Within days, a series of anonymous screenshots began circulating in closed astronomy forums. They showed grainy, compressed images supposedly from the recovered frames. Each displayed a bright arc curving around the solar limb, luminous against the coronagraph's dark mask. At first, skeptics dismissed them as digital fabrications, but spectral analysis of the JPEG artifacts revealed compression patterns consistent with NASA's image processing pipeline. The screenshots were real. What they depicted defied explanation. The arc wasn't random scatter or lens flare. It had structure-segmented nodes connected by faint filaments like beads on a glowing wire. The curvature matched exactly the predicted path of 3i Atlas. It looked less like a comet trail and more like a controlled turn. The discovery reignited debates that had quieted since December. If those frames were authentic, then 3i Atlas hadn't merely slingshotted past the Sunday. It had performed a maneuver, something deliberate, smooth, and energy efficient. The kind of trajectory correction used by spacecraft performing gravity assists. Physicists tried to model the curve using natural dynamics. None fit. The acceleration required was orders of magnitude beyond what solar radiation or outgassing could provide. The path was simply too clean. ESA refused to comment on the leak. When journalists asked for confirmation, the agency replied that all recovered data remains under review pending photometric calibration. The phrase became infamous in astronomy circles, shorthand for, "We saw something we can't explain." By March 2026, the screenshots had spread beyond niche forums to mainstream media. Articles with titles like "Interstellar Visitor Defies Gravity" and "Did NASA Hide a Solar Flyby" flooded headlines. Within days, official sources began issuing quiet denials, insisting the images were misinterpreted, optical noise. But by then, the narrative had escaped containment. Citizen scientists reconstructed the frames using brightness overlays and motion interpolation. Their composites showed what appeared to be a luminous curve bending gracefully around the Sun and exiting at an angle precisely 4 degrees off its previous inbound path, matching the later orbital data. That figure, 014 degrees, had appeared before in the DSN radar update logs. Different instruments, same number? Coincidence rarely repeats itself with such precision. The realization hit the community like a shockwave. It meant the radar data and the recovered images were describing the same maneuver from two different perspectives: optical and radio. One measured motion, the other measured echo. Together they formed a complete picture. Something had changed course near the Sun under its own control. The question now wasn't whether it happened. It was who or what made it happen. NASA doubled down on silence. But a few scientists within ESA began hinting in interviews that the phenomenon might represent a new category of object, entirely a hybrid between natural and artificial self, regulating but not self-aware. In other words, a machine without intent operating on physical principles we don't yet understand. That explanation satisfied no one, because if 3I Atlas was simply a natural reactor of physics, why did its path match human engineering so precisely? Why did its light respond to radar pulses? Why did its brightness fade exactly when it changed direction? And why did every attempt to observe it directly result in missing data? Too many coincidences form a pattern. As the controversy deepened, public attention began to fade. New discoveries eclipsed the story solar storms, exoplanet findings, lunar missions. The media moved on. But within specialized scientific networks, the discussion continued quietly, and with increasing unease. What bothered most researchers wasn't the question of extraterrestrial technology, it was the precedent. A single unexplained object had slipped through the most heavily monitored region of space in the solar system and left behind no consensus. For agencies built on precision that was unacceptable. In April 2026, NASA formed an internal review group called the Transient Object Analysis Committee. Officially, its purpose was to consolidate data from 3I, Atlas and Oumuamua to improve predictive models for future interstellar visitors. Unofficially, it was damage control. The committee met privately. No live streams, no press briefings, only encrypted minutes. Its existence was confirmed only because of a brief budget line in NASA's fiscal report Interstellar Object Trajectory Evaluation Discretionary. The committee's findings were never released, but a summary leaked to an astronomy journalist weeks later. It consisted of only 3 sentences. Observed deviations exceed modeled variance by 2 orders of magnitude. No satisfactory natural explanation consistent across all datasets. Further study deferred pending future detection of comparable phenomena. Deferred, in bureaucratic language that means shelved indefinitely. Meanwhile, amateurs noticed another strange development. Several online repositories that had hosted the original 3I Atlas images suddenly went offline. Links that once led to public data returned 404 errors. When users contacted the hosting administrators, they were told the takedowns were due to data redundancy policy updates. But the timing was suspiciously coordinated. Multiple servers across different continents purged the same directories within hours of each other. The erasure extended even to academic datasets. A doctoral student from the University of Tokyo who had been analyzing the spectral data found her institutional access suspended without explanation. Her supervisor received a notice citing temporary embargo pending verification. Verification of what was never stated. For independent scientists, it felt like history being rewritten. For conspiracy theorists, it felt like proof. Yet beneath the paranoia was a quieter truth. Institutions were retreating from uncertainty. They couldn't afford another Oumuamua-style media frenzy, not with funding cycles tied to confidence. Better to bury ambiguity than admit ignorance. Still fragments of data survived in private archives, thousands of amateur images mirrored and re-uploaded under new file names. In those frames, the faint green hue of 3I Atlas glowed defiantly, a reminder that facts can outlast permission. By mid-2026, New telescopic surveys like Vera Rubin Observatory's Legacy Survey of Space and Time began scanning the skies with unprecedented sensitivity. Analysts hoped to catch another interstellar visitor soon, something that could settle the debate. But the months passed with nothing. No new detections, no new anomalies, and then in September, an automated alert triggered deep within the LSST's pipeline. A faint object had appeared near the outer edge of the solar system, moving too fast for a long-period comet, but too slow for an asteroid. Preliminary trajectory analysis labelled it Interstellar Candidate 003, its provisional designation 3I Borealis. To most of the world, it was just another blip in the endless sky, but to those who remembered the number 3 meant something. The first was Oumuamua, the second was Atlas, and now the third had arrived. The announcement of 3I Borealis reignited every dormant debate that 3I Atlas had left unresolved. But before new data could be gathered, some researchers went back to the original question. What if these objects weren't separate at all? What if they were stages of a single system, fragments or iterations of something that travels in cycles? Mathematically, the idea seemed absurd. The distances and timescales involved were astronomical beyond any feasible continuity. Yet one eerie similarity stood out. Both objects shared nearly identical inclinations relative to the ecliptic plane 32 degrees. For natural interstellar debris, random orientation is expected. For two unrelated visitors to share the same tilt bordered on impossible. That pattern suggested lineage or design, and when trajectory projections for 3I Borealis were extended backward through time, they intersected a corridor of space almost identical to 3I Atlas. Inbound path offset by only a few million kilometers. It was as if something had traveled through once then sent another along the same lane. ESA scientists quietly noted the coincidence but avoided comment. NASA referred all media inquiries to the newly formed Transient Object Committee, which declined interviews, but independent analysts began compiling overlays of both objects' orbits and found more than geometry connecting them. Both had exhibited anomalous accelerations near perihelion, both showed color shifts inconsistent with dust physics, and both vanished from radar contact earlier than expected. The symmetry was uncanny. If 3I Atlas was a scout, 3I Borealis might be the response. That was the theory spreading through underground research forums and encrypted mailing lists where disillusioned scientists shared unfiltered data. They spoke in cautious terms as if afraid the act of naming the pattern would summon attention. One post, later deleted but preserved in screenshots, summarized the fear succinctly. What if these are not messages but instruments? What if each object is a probe that rewrites the space it passes through so the next can follow? The phrasing echoed an older concept in theoretical astrophysics, pathfinding, by gravitational editing, a hypothetical method of interstellar navigation in which small autonomous craft subtly alter the density of the medium to create safe corridors for subsequent travelers. It was pure speculation. A thought experiment until 3I Atlas came along and changed its own orbit. By November 2026, those whispers had reached mainstream institutions. A leaked memo from ESA's Advanced Propulsion Group admitted that certain recorded anomalies in solar plasma density could theoretically indicate localized field shaping. The language was dry, bureaucratic, but between the lines it read like confession. And yet, despite mounting evidence, no agency dared draw conclusions publicly. The fear wasn't of aliens, it was of uncertainty. To acknowledge that something in our solar system had moved with apparent intention would unravel the very premise of predictable physics. Science survives by mapping chaos, not by surrendering to it. In the absence of answers, speculation filled the void. Some claimed 3I Atlas was an ancient relic, a dormant machine passing through to awaken others. Others argued it was natural, a self-organizing phenomenon arising spontaneously under certain plasma conditions like lightning without atmosphere. A few even suggested it was human, made a classified deep space experiment decades ahead of public knowledge. Each theory revealed more about the believers than about the object itself. Because ultimately the question wasn't what 3I Atlas was, it was what humanity needed it to be. Proof of company, proof of control, or proof of mystery. In quiet corners of the internet, researchers still sift through corrupted FITS files and checksum fragments from 2025, hoping to reconstruct the missing moments between its acceleration and disappearance. They know they'll probably find nothing new, but they keep trying because within that emptiness lies the only real discovery the object ever offered, that the unknown still exists. For all the calculations and conjectures that followed, The truth remains simple. A point of light entered our solar system, behaved in ways our equations couldn't explain, and left without leaving proof of anything except our own limits. We called it a comet because we needed a name. We called it Interstellar because we needed a category. But names and categories are walls we build against the dark. They make the unknown smaller, manageable, less frightening. 3I Atlas refused to stay small. It bent our definitions until they cracked. And in that fracture between knowledge and uncertainty, it left a reflection not of itself but of us, a species desperate to understand what it cannot reach.